Right. Hello, everyone. My name is Scott Wlaschin. This is a talk called Building Confidence in Concurrent Code Using a Model Checker, otherwise known as TLA Plus for programmers. So we'll be using a tool called TLA Plus that you might or might not heard of. My name is Scott Wlaschin, and I have a website, F# for Fun and Profit, which is about F#. This talk is not about F#. It's a completely different kind of thing, but it will have too much information. This talk, there's no way you can explain all this stuff in an hour. So I'm going to cram a lot of stuff in and really just to demystify things and just to make you see that this is not as scary as you might think it is. And it's a whole new tool that you might find useful. I will be sharing the slides later on, and I think the video will be available later on as well. So, okay, why am I focusing on concurrent code? You know, there's people who've written concurrent code, and there's people who've had weird, painful bugs in concurrent code. And the combination of these two people, the intersection, is a perfect circle. Everyone who's written concurrent code has probably had weird, painful bugs. Now, you can get weird, you can get normal bugs in normal code, but they're not as weird and not as painful as bugs in concurrent code. So how can we, get confident about our code? We want to get confident about concurrent code. We want to get confident about, regular code. How many people actually are confident about that code? So I did a poll, and I asked a new programmer, what do they think of their code? And they often say something like, this code doesn't work, this code doesn't work, and I don't know why, because I'm a new programmer. I don't have a lot of experience. So no confidence there. Now, if you ask a battle-scarred veteran programmer who is kind of grumpy all the time, they will often say, this code works, and I don't know why. They just don't trust that their code works, even when it does work. So, you can lack confidence in your code, even if you're a very experienced programmer. So, this is a bit of a problem. So what do we do as developers? What do we do to improve our confidence in our code? Well, we have a lot of things to do at the design phase. We have domain-driven design and behavior-driven design and rapid prototyping and UML diagrams and all this stuff. All this stuff is trying to make sure we're doing the right thing before we start coding. And then when we're coding, we can use a statically typed programming language to avoid stupid things like nulls. And we can have good, well-debugged libraries. And then we have testing, which helps, you have test-driven development and property-based testing and canary testing. All these things improve the confidence in our code before we put it into production. So I'm going to introduce you to another tool, which is model checking. And as I said, the goal of this talk is to show you a different way of thinking about checking your code. It's another useful tool for your toolbox. It's not meant to be a replacement for everything, but it's just another thing to add. And it's very, very valuable in certain circumstances. And what do I mean by model checking? So here's a model. This is an architectural model. Every engineering discipline uses models of various kinds. And a model is a tool for thinking. The idea is you make a model and you look at it and you say, is this what I want? You can check things, make sure they make sense, make sure that everyone else is happy with it before you actually do the costly implementation. So with a building, you have a model before you actually start the construction process. But even for software, if you spend a few hours playing with a model, it's still a lot cheaper than spending a couple of weeks doing the implementation. So models are always a good tool. And like I say, it's a way of, it helps you think about your design clearly before you kind of get bogged down by the implementation details. So what is this model checking thing from a software point of view? Well, we're going to build a model using a special sort of domain-specific language, and then we're going to check the model. And there's a model checker that checks the model, and it checks things like, are all the constraints met? Does anything unexpected happen? Does it deadlock? All the different things that you might want to check. Is the model consistent in some way? You want to check this, and the model checker will check that for you. And this is really a whole part of the formal methods approach to software engineering. This is kind of one subsection of that. And it's actually very convenient to do. It's not as scary as you think. So currently, I think I would say the two most popular model checking systems are TLA Plus, The model checker is actually called TLC, but I'm just going to call it TLA plus everywhere just to be consistent, really, to make it easy. And it really focuses on temporal properties. It's excellent at that. And so it's really good for modeling concurrent systems. You can model all sorts of stuff, but concurrent systems in particular are very good. There's another one called Alloy, and the model checker is called Alloy Analyzer, and it focuses on relational logic, and it's really good for modeling structures. They're both very good. TLA plus is the one we're going to use today because we're going to be talking about concurrent systems, and TLA plus is excellent for that. So this is what some TLA plus code looks like. And the first time I saw this code, I thought this is the weirdest looking programming language I've ever seen. And the reason why it's a weird looking programming language is because it's not a programming language. That's why it's weird looking. It is actually mathematics. Shh. Anyway, so by the end of this talk, you should be able to make some sort of sense of this code. Not necessarily, obviously, be able to understand it completely, but it won't look quite as intimidating. So I'm going to try and do some live polling here. There is a link here, bit.ly/TLA poll, bit.ly/TLA poll, and I want you to type that into your browser if you're following along. And I'm going to see if anyone is listening, and let's see if we can get any results on this. So bit.ly TLA poll. Let's see if we have any results here. 100% of people can see this poll. Wow, that's amazing. Nobody says they can't see it. That's very good. Excellent. So just go back to, for the people who didn't see it, it is bit.ly TLA poll. And I'll be doing some more questions in a minute. So please get ready and type this in, and I'll provide the link again if you didn't get it. bit.ly TLA poll. And yeah, 100% score on the poll. That's awesome. Good. Okay, now let's go on. So who can see this poll? 100% of the people. Very good. All right, so what I'm going to talk about is confidence. I'm going to talk about TLA plus, and then I'm going to use TLA plus to solve some examples. I'm going to use a very, very simple model, and then I'm going to do a producer-consumer model and a zero-downtime deployment model, and I'm going to try and squeeze all of this into an hour. I think I will go over by a couple of minutes, but I'll speak very fast. All right, so part one is confidence. Confidence is a preference for the habitual voyeur of what is known as, sort algorithms. Here is a specification for a sort algorithm. To sort a list, if the list is empty or has one element, it's already sorted, so just return it. If the list is not sorted, take the first element and divide the other elements into two piles, one less than and one greater than. And then sort each of those piles in turn. And then the final result is the whole thing by concatenating the smaller list sorted, then the pivot element, and then the bigger list sorted. Okay, so how's your confidence level on this? How can you have confidence that this algorithm is correct? Okay, now not the implementation, but this algorithm. Is this algorithm right? Does it work? How would you do that? How would you get confidence in this? Let me ask you before I tell you how I would. So who thinks this is a correct specification for a sort algorithm? And I think I need to move to the next question over here. There we go. Right, who thinks it's the correct implementation? Who's not sure? This is live polling. This is very exciting. A lot of people are not sure. Yeah. I think that's where we are right now. Yeah. So that's not, there you go. This is life in the big city. So most people are not very confident. So what could we do? And in fact, you're probably right to be not confident because that's actually a logic bug here. This should be less than or equal or greater than equal, one of the ways, because we're throwing away duplicates. So that's actually a logic bug. So how can we gain confidence? Well, one thing is to do code review and careful inspection of the code and just have someone else go through it line by line. That's not a bad approach. One way is to actually create an implementation and then test that implementation. And that's not necessarily a bad approach either. For example, property-based tests would be perfect for this. And the final way would be to use like a mathematical proof assistant tool like Coq or something. And that is probably overkill really for something like this. Now, so personally, what I'd probably do is use code review and careful inspection of the code. And then things like property-based tests would be a fantastic way of finding bugs in this kind of code. It will probably find this bug straight away. So for linear single-threaded code, the tools that we have, the tools that you're used to, work pretty well. Now, how confident are you when concurrency is involved? Okay, so if you're not confident about a sort algorithm, how confident are you about something more complicated? And generally, people are very unconfident about concurrency. So here we have a queue, and the producer writes to the queue, and the logic we're going to do for the producer is they're going to check if the queue is not full, and if it's not full, we're going to write the item to the queue. And we're going to do it in two separate steps. It's not going to be an atomic step because otherwise it wouldn't be a very interesting problem. And then we have the consumer reading from the queue, and they do the same thing the other way around. If the queue is not empty, they can read. And if the queue is empty, they can't read. And so they're just going to loop doing that. So we have a producer and a consumer. Right, so here is the spec. And we've got one producer. We're going to start off with one producer and one consumer. And we have some constraints that we must never break. We must never try to read from an empty queue, and we must never try to add to a full queue because the whole system will crash and burn and it'll be a complete disaster. Hopefully our system's a bit more robust, but in some situations, you don't want to read past the end of a buffer, for example. So here's the spec again, basically check step and then write step. And on the consumer side, you do a check step and then you do a read step. Okay, so who thinks that this spec is correct and the constraints will always be met? Let me go back. I have to move the poll forward here. So there you go. What is the confidence in the design of this producer-consumer system? Right, so who thinks it's not correct, who thinks it is correct, and who's not sure? And it's a trap, by the way. This is a trap question. It's a trick question. Anything with concurrency is a trick question. Because you're never quite sure, is this the right answer or not? So we have, we have it, let's see. Some people are confident it's not correct. Some people are confident it is correct. And some people are not sure either way. But you just never know with concurrency. It's kind of scary. Yeah. So it seems like not that many people are sure that it's correct. And there's a lot of people who are confident it's not correct. And a lot of people who are not sure either way. Now, I'm not going to tell you the answer. We're going to actually use a model checker to check this later on. But I do have a question for the people who said they were not sure, and I'm deploying this to like a mission critical system. How could I persuade you? How could I make you confident? How could I say, yeah, I changed my mind. I am really 100% sure, or I'm 100% not sure. I mean, 100% confident either way. What could I do to give you confidence? Think about that. Now let's change the logic so we have two producers and two consumers, right? The first one had one producer, one consumer, and we'll do the same poll again. And you tell me if the producer consumer with more than one client, or, everyone seems to think it's not correct. So it's exactly the same. Producer, consumer, both do things. You want to make sure you never overrun the queue or underrun the queue. And there's two producers and two consumers. And most people seem to think it is not correct. And that's because you're scared of concurrency. That's good. So for the people who voted not sure, again, how could I persuade you? And for the people who thought it was incorrect, I come along and I say, okay, I have a fix for this that'll solve this problem. How can I persuade you that that fix is actually correct? I mean, you're not very confident that this is correct. What would make your so I have this magic fix. I'm going to use locks or something. How would you be confident that my fix was correct? What would make you confident? That's a tricky problem. So being confident in concurrent systems is really hard. And so all the tools we normally have for gaining confidence don't really work for concurrency. If we try and do careful inspection and code review, our human intuition is just rubbish for concurrency, really bad. If we try and create an implementation and test it, that doesn't work very well either, because many concurrency errors occur, 1 in 1,000 times. They might never ever show up. And we could use a mathematical proof assistant, and that's basically what we're going to do, except we're just going to do a model checker. It's a mathematical concept, but it's not actually doing a full-fledged proof. It's just going to check the model for consistency. And that's a much, much easier approach. And that's what we're going to talk about right now. And as I said, we will revisit the producer-consumer problem later on and check it for ourselves. So that brings us to TLA+. And again, I'm going to go through this quite quickly. Don't worry if you don't understand it. The goal is really to demystify TLA a bit for you. So stand back. I'm going to use mathematics. TLA+ is not a programming language. It's a mathematical way of doing things. So TLA is designed, or TLA+ was designed by Leslie Lampert, who you might have heard of. He's got a famous time and clocks paper. He invented the Paxos algorithm for consensus. He's a Turing Award winner. And he is the initial developer of LaTeX. And there is a photo of him. The LaTeX thing is relevant because TLA+ uses the same kind of syntax as LaTeX, which is, so it's going to look familiar if you're used to LaTeX, and it's going to look weird if you're used to programming languages. So TLA+ stands for Temporal Logic of Actions plus some stuff. So let's break that down into those words. The logic part, that's something to do with Booleans. So that's straightforward. We know how Booleans work. Temporal means something to do with time. And actions, in this case, is going to be transitions of a state machine. So if you think of TLA as a system which is a Boolean logic of state transitions over time, it sounds less scary. I'm going to explain exactly what that means. It's not as scary as you might think. And there's some other stuff too, which we will come to later on. So let's look at the logic part in TLA+. So the logic is Boolean logic, and hopefully you all know how that works. You've got and or, and not. And the mathematical symbols are upside down triangle, triangles up and down for and. It's easy to remember that the A in and matches the triangle. So it looks like the letter A, and the upside down triangle is or. And in programming, we use ampersand and vertical bars, but TLA+ uses the mathematical style, and that's why it has these weird forward slashes and backward slashes everywhere. That is just the and the or from TLA+, but the mathematical style TLA+. Now, when you run it through a nice formatter like LaTeX, it comes out looking like the mathematical style. So the code kind of looks ugly, and it gets formatted much more nicely by the time you're finished. Now, another word I'm going to use a lot is a predicate, and that is just an expression that returns a Boolean, a test, if you like. In a programming language, a predicate or a test looks like this. You have a function, and it's an A and B, or A and not C. And in TLA+, you would write it the same way, but using the different symbols. So you say A and B, or A and not C. So the symbols are different. The way it looks is very different, but the concepts are exactly the same. So if you've written a program that does a test, a function that does a test, you can write TLA that does tests exactly the same way. So, okay, now what about the actions? So the actions in TLA are state transitions. So what do I mean by a state transition? Well, we're going to model our system as a bunch of different states and the transitions between them. So here we have state A and state B, and we can go from A to B, and we can go from B to C, and we can go from B back to A again. We can't, from state C, we can't go anywhere. So this is like all the different things we can do in this system. Like a chess game, you say it's white's turn, and after white's turn, we transition to black's turn, and after black's turn, we go back to white's turn, and if white wins, the game's over. And once the game's over, you can't transition anywhere. Or a delivery system where it's undelivered, and then it's out for delivery, and then it's delivered. And once it's delivered, you can't transition anywhere, and so on. So this is a great way to model most processes. We're not talking about millions and millions of states. We're talking about, a few states to model. and all the transitions. So it's something you can kind of keep in your head. So in TLA, here are 2 states and 1 transition, and it's going to transition from hello to goodbye. And this is the state before, and this is the state afterwards. And in TLA, you would write it like this: state equals hello before, and in the state afterwards, you'd write state tick equals goodbye. So that little tick means afterwards. Mathematicians would call that state prime equals goodbye. That means it's some kind of a modification of the original state. So every time you see that tick, that means it's the after state. And if you don't see the tick, it's the before state. So the action is the transition, and this is how you would write it. Let's say we have a transition called next. In TLA, we define it like this: next equals state equals hello, and state prime equals goodbye. And in English, we'd say the state before is hello, and the state after is goodbye. Now, this equals is not an assignment, it's an equals. It's like, is the afterwards state equal to goodbye? So this is a test, it's not an assignment. And you can prove that it's a test because if you swap these 2 segments, that works just as well from a logical point of view. The afterwards is goodbye and the before is hello. That's exactly the same thing. That doesn't work with programming languages, but it does work with logic. So this is really important. Actions are not assignments, they're tests. So here we have a test. Is the state before hello and the state after goodbye? If it is, that's good. But here, when it doesn't match, the state afterwards is ciao, that doesn't work. Here, the state before is howdy, well, that doesn't work either. So it's testing whether the states match the condition to do the transition. So that's what an action is. Right, now let's look at the temporal in TLA+. Temporal for time. So TLA+ models the state transitions over time. In fact, over an infinite amount of time. Imagine a little clock ticking, 1 second, 2 seconds, 3 seconds, 4. Each time you transition to a different state. And of course, time goes on forever, and so the states go on forever too. And because of that, you can ask questions like, is something always true for every single possible state? Is something ever true? Is there one state where it becomes true? And if something happens, does something else have to happen afterwards? Those are temporal questions. Those are questions that are over time. And TLA is excellent at answering those kinds of questions. So temporal logic of actions, same as Boolean logic of state transitions over time. So just one way to think about it. So that's everything you need to know about TLA for now. And we will save the plus for later. Okay, now let's move on and use TLA plus to build a very, very simple model. And the model we're going to pick is counting to 3. That's how complicated this model is going to be. So I bet your programming language can't do that. So, okay, let's look at counting to 3. We have 3 states. We start in 1, and then we go to 2, and then we go to 3. And in a programming language, we say x equals 1, and then x equals 2, and then x equals 3. So that's very, very exciting. Let's see how we would do the same thing in TLA+. So I'm just going to put the code down. This is what the code looks like. And then I will explain what it means. So the first thing is we have an initial state. State machines can always be described by saying, what's the initial state, and then what are all the transactions to go between the states. So initially starts with x equals 1. And then the next transition is x equals 1, and afterwards x equals 2. And the next transition is x equals 2, and then afterwards x equals 3. And then the overall next thing is matching either of those transitions. It's either the first one or the second one. So the overall complete set of transitions we can do is the first one or the second one. So we're going to define the next operator to be that. All right, so that's our complete TLA plus spec for counting to 3. Now let's do a quick refactor. What we've done here is we've created 2 helper functions, as it were, 2 new steps, just to make life a bit easier. And these things are not really functions. These are actually called operators, and you can actually think of them as more like macros. They're literally copy and paste kinds of thing. You could take them and copy and paste them around. So after we've got these we've kind of pulled these out into their own steps. the overall next step is a lot easier to read. It just says do step 1 or do step 2. So this is a little nicer to read than the first version. Okay, so that's our complete spec for counting to 3. Now let's show you how to run it. So the best way to run it is probably something called the TLA Plus toolbox, which is sort of the IDE, the TLA Plus. There is an extension for VS Code, but you sort of have to know what you're doing. The TLA toolbox has a nice user interface. It's written in Java. It's kind of a bit of a 90s user interface. I wouldn't say the user interface is the best part about it, but it does work. So you type your code into a editor there, and you run it and you make sure there are no syntax errors. That's the first bit. Okay, so now we've got our code. Now we create a model, and for a model we have to say what's the first state and what's the next state. What's the state transition. So we just say to the model, okay, you start with init and all the possible things you can do are next. And then we click the run button and it runs the model checker. And what happens? Well, first of all, it detects that there are 3 distinct states, which is good. That's hopefully there are 3 distinct states. And then it also says deadlock reached. And that doesn't sound very good. That sounds a bit scary. What does it mean by deadlock? So we go and look at the error, and there's a little trace, and it says it went from 1, and then it went to 2, and then went to 3, and it stopped. And this is the problem. The problem is that it stopped. It went to 3, and there was no forward progress that could be made here. And if you can't make any forward progress, if there's no valid transition that you can do, that's what TLA Plus calls a deadlock. Literally, you're just stopped. And so in this situation, our count to 3 example, it deadlocks when it reaches 3. So that's not very good. So the main thing here is it's really important to be aware that these state machines really do have to be infinite series of state transitions. Over time doesn't just stop. You know, after 3 seconds at state 3, but where should it be at 4 seconds and 5 seconds and 6 seconds? You've got to tell it. So in our case, well, we're done when we hit 3. So let's just have a transition that, okay, when you're at 3, you can go to 3 again, and then you can go to 3 again, and then you can go to 3 again. And you can just keep looping at 3, and then we're done. Okay, so let's add that to the model. We're going to add a little loop on the 3, and we're going to add a new step called done. So to say that you just don't do anything and you just stay put, you can say there's a special keyword called unchanged. So the X is unchanged, it just loops back on itself. So now we have the loop, and we have this new final step saying it's done when X equals 3, and at that point, it just stays unchanged. So the overall thing is now 3 steps. It's either step 1 or it's step 2 or it's done. Now, if we run this new model against with the model checker, it sounds great. No deadlock, everything's happy. Okay, so that's a very complicated way of counting to 3. Now, one thing before we move on is I should just point out that doing nothing is almost always an option. Let me show you 2 different infinite series of states. Here's a state machine that counts 1, 2, 3, and 4, 5, whatever. Here's another one. Now in the first one, you may say, well, this one runs every second. 1, 2, 3. The second one, a millisecond after the first one, nothing's happened. It just transitions from 1 to 1 and 2 to 2 and 3 to 3. And really, is there any difference between these 2 systems? From a time point of view, I mean, every second the clock ticks and it goes from 1 to 2 to 3. And the fact that nothing happened between one, in a millisecond, really, they're exactly the same system. And so they need to be modeled as the same system. And pretty much staying in the same state is almost always a valid state transition. And TLA has a word for that called stuttering, meaning you're just not doing anything. You're just sitting around, not making any progress. So we need to add stuttering. It's always good practice to add stuttering to your model. So we're going to add stuttering. So you can hang around in 1 and you can hang around in 2. And we just add that again to our next step. You see there's step 1 or step 2, or it's done, or nothing changes. Okay, so that's the added stuttering now. So our model, we're building up our model. We're adding new things to a model. So now let's talk about time. So we've got a very complicated way of counting to 3. It's not very exciting, but that's not the point of using TLA plus. The point of TLA plus is it can do a lot more than that. And so let's start doing these extra things that your programming language can't do. We're going to check some temporal properties. Temporal properties, properties that have some sort of meaning over time. Okay, so a property applies to the entire system over time, not just to any individual state at any one time. And so checking these kinds of properties is really, really important. And this is the kind of thing that humans are really bad at. Checking that the queue size, it never goes out of bounds. It's really hard for us to kind of see that when you have multiple producers and multiple consumers. Programming languages are really bad at this too. An average programming language is not designed for this kind of thing. However, TLA plus is designed for this kind of thing. TLA plus is excellent at this kind of thing. So let's use TLA plus to do it. So what kinds of properties can we check? What's useful in our world of modeling? Well, a very important property is that something is always true. Right? Well, you want to make sure that in our, in the queue case, that the queue never goes below 0. In our count to 3 example, we could say that the queue that our number x is always greater than 0. It goes 1, 2, 3. If it goes below 1, something went wrong. Another useful one is something is eventually true. In our case, is it true that at some point in time x equals 2? Well, yeah. Is it true at some point in time that x equals 42? No, it isn't. Eventually always is an interesting one, and you use this for where something is done. So when it eventually something becomes done, it's not always done, but eventually it does become done. But when it does become done, it stays done. In our case, x eventually becomes 3, and then it stays there. It's done. At that point, our counting to 3 is done, and it just kind of loops around, staying at 3. So that's what's called eventually always. And another useful one is leading to. So if x ever becomes 2, then I guarantee it will become 3 later. But if I said if x becomes 3, I guarantee it will become 1 later, that's not true. So we have to kind of formalize this because we're using kind of informal language. So we need to kind of into kind of mathematical language. So in English, when we say something is always greater than 2, we really mean that it's always true that x is greater than 0. And in TLA, we use the kind of square brackets as the always operator. When we say at some point x is 2, the more formal way of saying that is it's eventually true that x equals true, that x equals 2, that's in some state. And again, in TLA plus, there's a special operator for that, which is the angle brackets one. X eventually becomes 3 and then stays there. That's one of these eventually always things. So it's true that eventually always x is 3. So always x is 3 is not true at the beginning, but eventually it is true. And the symbol for that in TLA plus is the angle brackets followed by the square brackets. And then finally, if x ever becomes 2, then it will become 3 later. That's in TLA, we use a kind of wiggly arrow for that. So those are kind of really important properties that are all sorts of uses, and we will see this used later on when we come to the more complex examples. So let's add these properties to the script. Always x is 1, it's greater than 1, it's less than 3. So it's always within bounds. So we're going to use the square brackets for always, and then we just say x is greater than 1 and x is less than 3. That's always true, no matter what state it's in. At some point, x equals 2. So we're going to use the angle brackets. At some point, eventually, x equals 2. At some point, x equals 3 and stays there. So this time we use the eventually always, which is the angle brackets followed by the square brackets. And then whenever x is 2, then x does become 3, and we use the twiddly arrow for that. Okay, so that's the properties. And in the model checker, we kind of have to tell the model checker that we want to check them. There's a little bit of a user interface. We can do that. So I want to check all these 4 properties and make sure they're always true, no matter how I run the model. So here we have the properties again, and we're going to ask another poll. How many of these properties are true? And let me go to the poll thing here. How many of these properties are true? All 4 of them, some of them, one of them, or none of them? Okay. So, and I promise you, I haven't made any typos. This is the correct way of specifying these properties. So it's not a typo kind of thing. It's like from a logical point of thing, will these properties always be true? So this is your confidence test. And most people seem to think that all 4 of them will be true. And a couple of people think that some of them will be true. Okay, so it's TLA, it's bit.ly/TLA poll, if you're following along at home. And yeah, I think I'm just going to say vast majority of people think that all 4 are correct. Some people think that some of them are correct. Nobody thinks that anything else is right. So yet again, your intuition is wrong. Because if we actually run this, we run this little thing and the model checker says, uh-oh, temporal properties were violated. Now, what happened? Well, if I look at the trace, it says it started at 1 and then it stayed at 1 and then it stayed at 1 and it stayed at 1. It stuttered. It just kept going round and round. What we've got here is we've got an infinite loop, because you forgot that I added this infinite loop to the 1 state. And this is really easy to do. And so what happened here is that it never got out of the first state. And so none of the other properties were true. One of the properties was true, which is the bounds. Was it always within bounds? Yes, it was. It was always, greater or equal than 1 and less than or equal to 3, because the very first state, that was true. But none of the other ones came true because it never left the first state. That's kind of annoying. We went to this trouble to add this stuttering thing because we're supposed to add it to represent a good model. And yet as soon as we add it, it complains that it's just stuck in an infinite loop. That's not very helpful. So how can we fix this? What we want to do is, it's okay. I don't mind if you go around that loop a few times, but I want you to at least try some other things. Don't just go around the same place forever. Try some of the other transitions once in a while. So that's what we wanted to do. And there's actually a word for this. This is called fairness. Don't just pick on one transition and stick to it. Try all the other transitions. Give all the other transitions a chance. Don't just don't stick with one of them. So of course, TLA plus can model this. And so let's see how TLA plus does model it. So how do we model fairness in TLA plus? We have to do some kind of bit of code refactoring again, and then we can add the fairness. And unfortunately, the syntax for this gets a bit ugly, so just bear with me. The first thing we have to do is get rid of the initial and next transitions and merge them into a single specification which encompasses everything. So rather than saying, here's the initial one, here's the next one, we're going to have something that combines both of them. So we're going to say the overall specification is going to be the initial step, the initial state, and then always something else, some sort of state transition. Okay. Now the state transition is either the next transition or the unchanged transition. So it's either do the next step or do one of these infinite loops, and always do one of the two. So that's the overall specification, the way we have it right now. Okay, so this is what it looks like right now, but then there's a special syntax for that to make it look nicer, and it looks like this. So that's what it looks like before, and that's what it looks like afterwards. This special syntax, when you have the little underscore, that means stutter on X. So it says try to do the next transition or stutter on X, and they're both good. All right, so that's what we've got right now. Now, finally, we can add the fairness constraint. And this is what it looks like, WF underscore X of next. And I told you the syntax is a bit kind of gnarly. This is called weak fairness. There's actually another one called strong fairness, and I'm really not going to get into the difference. But what this basically says is don't keep going round and round in circles. Try doing the next transition every so often if it's available. Just don't get stuck in a loop. That's all that means. So here's our complete spec with fairness now. We've added the fairness constraint. And here are properties to check. So this is the complete spec now for counting to 3. And if we run this new spec, all 4 temporal properties are now true, which is great. So what we were missing, we just needed to add that fairness thing to make sure it didn't get stuck in a loop. And these properties are true, just as we thought they would be originally. That's nice. So now we're done. So we can count to 3. That's very exciting. Now, this is the thing. So counting to 3 is not the exciting part. What the exciting part is that these 4 properties checking whether something's always true, eventually always true, and so on. These are the things that you can do in TLA plus that you can't do in a programming language. So this is really the point I want to make about this little example. You know, this is the stuff that's the critical stuff. Okay, so now let's move on to the producer consumer examples that we did earlier in the talk, and let's see if we can model them and get confidence rather than everyone saying, well, I don't know, I'm not sure, I don't have a lot of confidence. Let's see if we can get rid of that and get some confidence. So here's the examples again. We write to a queue, and we've got two different stages. We read from a queue, and we have two different stages. So now what we're going to do is make a model of this in TLA plus, and we're going to check the model and see what the model says, rather than just guessing. So on the producer side of things, there's actually two different states. We start off, we're ready to write, and then we can see, can we actually write? Is the queue full or not? If the queue's not full, we can transition to the write stage. And then at that point, when our turn comes around again, we can try writing. And after we've written something, we go back to ready and we start all over again. So as I said, we're going to model this as two distinct transitions rather than one atomic step, because if it was one atomic step, it would be a really boring example. So the programming language version of this, if I was doing this in like Python or some sort of pseudocode, this is not exactly Python, but if the queue size is less than the maximum size and we're in the ready state, then we can transition to the write state. That's the first bit. And then the second bit is if we're in the can write state, then transition back to the ready state, and as part of that, change the queue size, push something onto the queue. Now, since this is a model, I actually don't care what the contents of the queue is at all. The only thing I really care about is the queue getting bigger or is it getting smaller. So we're just going to, in our model, we're just going to use the queue as an integer. We're just going to add one and subtract one every time we read and write. That's good enough to test our model. There's no point making it more complicated than that. So that's the programming language version. Now let's look at the TLA plus version. So same kind of thing. If you're in the ready state and the queue size is less than this, and now this is again, it's not assignment. So all three things have to match for this transition to be valid. Okay. So afterwards, the producer state's in write, and the queue size is unchanged. Now this is one of the differences between TLA and a programming language, is that every variable has to be accounted for in a state transition. You can't just say, I don't care what happens to the queue size. You have to specifically say either I am changing the queue size or I'm not changing the queue size. You have to specifically say that always. So I have to specifically say the queue size is not changing. Okay, so that's the first bit. Now the second bit, similar kind of thing. If I'm in the write mode and I can transition to the read mode, to the ready state, and I can add one to the queue. And those are the two different transitions. Now, overall, as a producer, the two things I can do is I can either I can do the first transition or the second transition. I can do the check part or I can do the write part. So it's this or that. It's the upside down triangle. It's or. So that's everything I can do as a producer. Now, let's look at a consumer. It's pretty much the same kind of idea. We can check whether it's readable. If the queue size is bigger than 0, I can read. Otherwise, I can't read. And I transition to the can read state, and the queue size is unchanged. And then when I actually do a read, I have to start off in one state, and then I transition to the other state, and at the same time, I take something off the queue. So that's the check and the read for the consumer. And again, the consumer as a whole has two parts. It can either do the check or it can do the read. So it's or. So we've got the consumer action and we got the producer action. So if we combine them, I'll just show the entire valid script here. We have to also, in a proper TLA script, we have to list the variables we're using. And I'm going to assign the maximum queue size to be 2. It's a model. It doesn't need to be like 10,000 long. It just needs to be a few long, because that's all we need to check all the possible states. So the initial state is that both things are ready and the queue size is 0. And then the producer will start, this is the same code I showed you a minute ago for the producer. And then this is the same code I showed you a minute ago for the consumer. And then finally, the overall all the possible state transitions we can do is either we can do a producer action or we can do a consumer action. So we got choice between the two. Now, what's interesting is when we write this, we've actually got a non-deterministic system. We've got, you might think of it as two different processes or two different threads or two different actors. They're kind of running in parallel. In TLA Plus, this is completely natural. I don't have to like create a special thread or process or something. We just say these two things can happen. Either of these two things can happen at any time, and we get parallel behaviors happening at the same time, which is kind of cool. So that's one of the things that's really nice about TLA Plus. It's why it's so good for concurrency. You don't need to do anything clever to get kind of concurrency happening. Something else I should point out is that we don't have any stuttering, because this system, these loops they'll go round and round in a loop. So there'll never be a point where there'll be a deadlock, hopefully. Should we add stuttering anyway, though? Should we add the fact that everything could stay unchanged? And that's a good question. And what happens if you think of things being unchanged, you could actually use this to model the system's crashing. Like if the producer isn't producing anything, how would you detect that? Could you handle that? Maybe you need to monitor the queue size, and if the queue hasn't changed size for a while, that's a flag or something. You can actually model that very nicely in TLA Plus. So that's kind of cool. So what are the properties? What are the properties we want over time for this model? Well, the main one we wanted was it was always within bounds. The queue size is always greater than 0, and the queue size is always less than the maximum. So you should be able to read this now. Queue size is greater than 0, and queue size is less than the max, and that whole thing is always true for every possible state. So if we run this, there's 8 possible states it can be in, and there are no errors. So that's great. So the invariant of the queue size being out of bounds is never going to happen with one producer and one consumer. We have a lot of confidence in this design, but with one producer and one consumer. So we're not guessing anymore. I trust that the model checker worked, and it checked all the states, and everything worked properly. So that's good. I have confidence for this one. Now let's do the concurrent one and see what happens there. So this is when we have more than one producer and more than one consumer accessing the same queue. And this is, now we need the plus part of TLA Plus, which is the set theory. So again, this is a mathematical thing. TLA Plus uses sets, and if we use a program language and we want to like filter out a subset of something, we would use a keyword, a method called filter or something. In TLA Plus, you'd say all the elements in the set such that this predicate is true, which is the mathematical way of saying it. If we wanted to find all the elements in the set where something was true, does there exist an element which is true? In a programming language, you would probably say, any. Is there anything in the set which is true? But in TLA Plus, we use mathematical conventions, and we say, does there exist an element X in the set S such that this predicate is true? So when you see all these /A's and /ins, that is set notation in TLA Plus. So it looks a bit scary, but once you get used to it, once you start recognizing for what it was, it's not as scary as you might think. Okay, so we're going to need a set of producers and a set of consumers, and we need to use the set description part of TLA Plus. So our code is going to get a little more ugly, unfortunately. So here we have 2 producers and 2 consumers. That's what we're going to pass in. So here's the specification for the multi-producer consumer one. Now we're going to have the producer state and the consumer state, but this time they're going to be dictionaries. They're going to be maps. I'll explain that in a minute. That's the same. Initialization is slightly different. So let me just take you through this. These are now a dictionary or a map where it's a bunch of key value pairs, and the key is the producer or the consumer, and the value is the state of that producer or consumer. So when we do something like this, what we're saying is for every producer, assign the value for that to be ready. So if you're used to Python or something, it's the same as that little bit of code underneath. P1 is ready, P2 is also ready. Now, to check whether something is writable, the code looks a little bit different as well. This is now parameterized for a particular producer. this code is now. So we can pass in a parameter to these things. And this now says the producer state at that key is that ready. For that particular producer, is the state ready? The queue size is the same. And now afterwards, the producer state is, we can't just update one part. We have to say the entire producer state is exactly the same, except for this one thing. So the new producer state afterwards is the same as the original producer state, except that one key value pair has been changed. And for this particular producer, the state has been changed to can write. So that's why it uses the word except, because it's the original set, except this one thing has changed. Similarly, on the other side of the right side, similar kind of logic. We update the state except for it's now ready. Now the producer action also looks different, because what we now have here is we have a lot of producers. So what we're going to do is try and find any producer that we can do one of these transitions. Does there exist a producer in the set of producers that we can do either the check transition or we can do the write transition? So we're just going to try and find any of the producers, and it doesn't really matter which one we pick. It's non-deterministic. Now on the consumer side, it's very, very similar. We have parameterized version of the readable thing. Again, it's now parameterized by consumer. The key value for that, we look up that consumer as the key, and if the value is ready, that's good. And again, when we update the state, it's exactly the same as it was before, except that the key value for this one has changed to can read. So that's what that logic is. And again, the read logic is very similar. So now we're just using set notation a lot more rather than individual things. And again, for the consumer side of things, we have to say, does there exist a consumer that can go to one of these two states? Can it read, or can it, can we do the check transition? Can we do the read transition? Is there a consumer that will do that? So if we run this script, we run the model checker with two producers and two consumers, and the same always with bounds property. There are 38 different states, 38 states. We can't possibly check 38 distinct states by hand. And we get this error. The invariant is violated. So this is not true. We are confident this design does not work, unlike before when we were guessing. So no need to guess. We can be confident that we're right or wrong. So TLA Plus won't tell you how to fix the error. You have to think, okay? But when you want to test the fixes, you just update the model with the fix. So let's say I want to make the operations atomic, or I want to add locks, or whatever it is. I update the model to do these things, and then I can rerun the model checker. And whatever the model checker says, I now have a lot more confidence that the fix does work or the fix doesn't work. But, my confidence is very high rather than just guessing. Like if I add a lock, is that going to work? Maybe if I have wrong logic for locking, maybe I have right logic for locking. Locks are tricky too. Now this is all in 50 lines of code. So this is a really nice little script that we can use for doing our checking our models. So, okay, last bit, I'm running out of time. I'm going to go a few minutes over. Sorry about that. But we're now going to use TLA Plus to do a zero downtime deployment. And this is kind of a real world example. I want to have a zero downtime deployment of a bunch of servers. Is my logic correct? Am I making any mistakes before I actually do it and have a problem? So I'm going to go fast. Don't worry about the details. I just want you to get the overall big picture of what you can do. So TLA Plus is a great tool for improving the design process, because you can do these kind of sketches in a few lines of code. You can check it, you can fix it, you can check it again, and you can repeat and repeat until you're happy with the design. And it's so much faster than writing real code. You can do things in hours or minutes rather than weeks or months. So if you think of it as like test-driven development, but for concurrency, instead of red-green refactor, it's red-green remodel. You get a red, your thing doesn't work, you make it work, you remodel it until everything is green, and then you're happy to go. So what we're going to model in this situation is a bunch of servers. Each server has to be upgraded from version 1 to version 2. Each server goes offline during the upgrade. And we want to check that there's always a server that is online, like zero downtime, and all the servers must be upgraded. That's kind of important. Like if they all stay at version 1, there's no problem. But we want to make sure they all go to version 2 at some point, otherwise it's not a very good upgrade. And I'm just crediting Hillel Wayne for the idea for this. here's a post on modeling deployments, which I based this example off of. So let's sketch the design. We have a server state in version 1. We start the upgrade, it goes offline, and then we finish the upgrade and it comes back online again as version 2. And then once it's a version 2, we're done, and we can just kind of loop around forever in version 2, just like we did with the count to 3 example. So this is the initial state. All the servers are online and in version 1. When we start a particular server, it goes, if it's in online and it's in version 1, all the servers state is the same except for this particular one changes to offline. And when we finish, it has to be offline, and afterwards, all the servers are the same except this particular one goes to version 2. So that is our model. Now, we're going to combine the start and finish into a single step called upgrade. And this says try and find a server where we can do either the start step or the finish step. So does there exist a server that we can do that? And then we're done if all the servers are finished. So if it's true that all the servers are in online version 2, we're done. And then we can just say, yeah, we can just do our infinite loop at that point, which everything's unchanged after that. So that's the done state. And so overall, the entire next is either do the upgrade step or do the done step. And that is our entire sketch for the logic for upgrading our servers. So like I say, I'm whizzing through this very quickly, but you know, you don't have to understand the example, the code too much, but I just want to show you that it's not that hard to like sketch out a design. Now, here's the thing, we want to check and see, does this work, right? So with one server, we have 3 states, which is probably what we'd expect. And the number of states goes up exponentially as you add more servers. And it's really hard to eyeball for errors. So we're going to do the model checker to make sure we haven't forgotten anything. So let's add some temporal properties. We want zero downtime. That's a really important one. And that means not all servers should be offline at once. And we want the upgrade to complete. So that means all the servers should eventually be version 2. So let's write the code for that. It's always true there exists a server that's not offline. So we say, it's always true that there exists a server that's not offline. Always there's a server where the server state is not offline. And not, it's / equals is TLA plus for not equals, like bang equals. Okay, what about the other one? Eventually upgraded. What does that mean? That means eventually all the servers, the state for that server is version 2. So that's the set logic and the temporal logic combined. It's eventually true that for all the servers, the server state is going to be version 2. That's what it means to be eventually upgraded. So let's run this script with 2 servers, and we get the zero downtime violation straight away because there's something wrong with our model. And the trace tells us exactly what went wrong. Server 1 went offline, and then server 2 went offline, and now they're both offline, and that's bad. So that invariant was violated straight away. Well, okay, I've got an idea. We could fix this. But how can we be sure that our fix will work? Well, let's check it with the model checker. So we're going to add a new condition for the starting an upgrade. We're going to say you can only start an upgrade if no other servers are offline. And that way only one server can be offline at a time. So this is this new transition. If there exists another server, which the server is offline, then don't start the upgrade. Okay. So only one at a time can be offline, and they can't all be offline at the same time. So other than that, it's the same. So if we run this model, the zero time now works. So it's always true that you never have any downtime. That's much better confidence. However, eventually upgraded fails. Okay, why does it fail? Because of stuttering. Because in our code, the model says it just stays at version 1 forever. Yeah, well, that's not very helpful. So the way to fix that is to add a fairness condition. And we add a fairness condition, and now it works. So if we do this, we now have complete confidence in this particular design. This is great. Now let's add one more condition. Let's say that all the servers have to be running the same version, which is a decent condition to have. They all have to be running either version 1 or version 2. So here's all the list of all the servers. Here's the set of servers, all the servers which are not offline. That's the set of online servers. And it's always true that you take any 2 servers in the list of online servers and they have the same version. Now, if you run the script with this property, we immediately get an error again, the same version. It's not always true. Well, why is it not always true? Well, because server 1 goes offline and server 1 comes back online, upgraded. Server 2 is still online and it's a version 1. So that it breaks straight away. So the model checker found a logic bug straight away with our design, which might not have been obvious. This is the kind of thing that gets more and more subtle. We might not have been aware of that if we hadn't checked it. Now, the classic way to fix this is to add a load balancer. So let's add a load balancer. We're going to add a load balancer variable, and it's just going to point to version 1 servers or version 2 servers. So the load balancer initially starts pointing at version 1 servers. So what do we mean by the online servers? Well, it depends on the load balancer. If the load balancer is version 1, it's going to, all the online servers are version 1 servers. And if it's not version 1, then all the online servers are version 2 servers. So that's our very crude model of a load balancer. That's about as it's a very simplistic model, but it's enough to check our logic. Okay, now when does it switch over to version 2? Well, when one server manages to switch over to version 2, we can then switch the entire load balancer over to point to the version 2 pool. So the load balancer, as soon as one of them successfully upgrades, we can start pointing the load balancer at that one, and then all the other ones can upgrade in their own time. So we switch over when one of them is finished upgrading. So if we run this script with the load balancer logic, everything still works. The previous ones still work, which is important to check, and the same version works. So all our constraints, all our properties are true for the entire system. And I have a lot of confidence that this is a good design. I can now code this and put it into production, with high confidence. So that's great. So this is the, I'm just going to go a few minutes over, sorry. The sketch is complete. You can think of TLA Plus as agile modeling. Like it just took a few minutes to do that sketch. And it saves, 10 minutes of doing a sketch as opposed to a few hours or a few weeks of programming. Definitely a good thing. Much, much more confidence. So some common questions before I finish up. How do you handle failures? Well, that's easy. You just add failure cases. So if the upgrade failed, how would I model that? Well, I just add a state called upgrade failed rather than, and we have to handle all those cases too. And a very common question is, how does this convert to code? And the answer is it doesn't. This is not a code generator. This is a tool for thinking. Just like an architectural model is not a blueprint. It's a tool for thinking about whether you've got the right thing. It's really about having confidence. So just like an architectural model is a way of checking, are you doing the right thing before you spend a lot of time doing the implementation. So to finish up, TLA and model checking is not that scary. It looks a bit scary when you look at the code, but the concept's actually pretty straightforward. Think of it as agile modeling and you'll be doing really well. And I think if you're doing any kind of concurrency systems, it's kind of really important to use it. Check it out. Having a good toolbox in your development arsenal is a good thing to have. TLA Plus can do a lot more than I showed today. It can do model checking, but it can also do refinements. It can do proofs. It can do a lot of stuff. I just scraped the surface today. For more information, there's a very good page, TLA Plus homepage. It's got a video. It's got a massive book, a lot of papers, and there's also learntla.com website, and there's a book called Practical TLA by Hillel Wayne, and he also does trainings. So you want someone to train your team in TLA Plus, contact him, and I'm sure he would be happy to do that. So thanks very much. I will put the slides up on my website, fsharp/fun-and-profit/TLA Plus. And if you are interested in other kinds of things, I have a book, Domain Modeling Made Functional, which has nothing to do with this, but I have to promote it anyway because I'm an author and that's what authors do. But please feel free to contact me on Twitter or contact me on the Slack, the NDC Slack afterwards. I'm happy to stay around and ask questions. And thanks very much, and see you next time.